Hey folks. All right, well, now that we've got the hang of arrays and of passing them as parameters to functions and letting the functions do all sorts of weird and wonderful things to them, let's try some searching and some sorting. So cases where we're dealing with a collection of data in an array and we're trying to find things in the array, or cases where we're trying to rearrange the content of the array to be in sorted order that we can take advantage of later on. So that's the plan. Let's see what we can do here. Now, again, it's pretty common for us to need to store a whole bunch of information. We store a whole bunch of data values that we're working with. We take 60 measurements of temperatures or something like that, and we store them all, or we store a whole collection of item prices, or whatever it might be, a whole collection of student grades or student marks, all sorts of different cases where we're storing a whole bunch of data. So for now, we'll assume that we're storing it in an array. We'll look at other more interesting data structures later on. But now that we've got arrays to play with, let's suppose we're storing things in an array and we want to go through and access data. So it's not uncommon for us to need to go through the array and find something inside it. Do I have a mark for student, whatever their student number is? Do I have a temperature reading that's -60? Do I have any item prices that are 105? Is there something that I need to search for? Is there a value I want to look for in the array? So we'll look at two searching techniques. One is called linear search, where we just go through everything and look at every position in the array until we either find it or run out of spaces to look. And the other takes advantage of sorted arrays, where if we know the data is sorted, we can come up with a much more efficient search called binary search. So these are the two things that we want to take a look at. And then we'll also say, okay, well, if it's handy to have our data sorted, then we need some way to sort. So we'll take a look at one sorting technique called a bubble sort, and maybe throw in one more routine at the end just to be able to say, well, if somebody gives me an array, can I check to see if it's sorted or not before I try and do things with it? So these are the things that we'll try and play with today. So this linear search is the first idea, where we're just going to go through every single position in the array. If somebody gives us an array and gives us the size of the array and gives us a value to look for, we'll just look in every position of the array from front to back. And conceivably you could go from back to front, but we'll go from front to back. Go through each position of the array from the first one to the last one, looking for that value. We can stop when we find it, but we have to go through the whole array to be sure it's not in there, right? If they give us an array of data values and ask us to look for a 17 and there's no 17 in there, we won't know that until we've looked in every single position. So this linear search, go from front to back, looking every place in the array. So this is the simplest one to work with. And again, the code is pretty straightforward. It's a basic loop, right? We're creating a search function. If they're telling us to search for a value in an array, then if we find it, they probably want to know where we found it. So what we'll do in our search is look through the array. If we find the value, we'll return the position where we found it. I found your value 17 in position 12. That way, they know where it is in the array. In the future, if they want to use it, they can, okay, it was in position 12, I'll just use position 12 anytime I want to access that value. Now, that's all well and good, but it's possible that we don't find the 17. Right? It's possible it's not in there anywhere. We still have to return some kind of an integer for them, but we want to pick a value that isn't a valid position. Right? It's got to be an integer, but it can't be a valid position. So most commonly, what we do in situations like this is to return a -1. Right? That makes it obvious that it's not a position in the array. Right? We can't have negative indexes, so indices. So we'll go through and use -1 as the default value. If I don't find it, I'll return a -1. That way the caller, they can call search and then check the return value. If the return value is -1, it wasn't found. If it's anything else, then it's a position in the array. So this is the goal. Again, our search routine is pretty straightforward. Let's say in this case we've got an array of floats, and they've told us how big it is, and they've passed a parameter telling us what we're looking for. So this time through, look through my array of 10 elements looking for value 17, for instance. And again, this is a linear search. We'll go through each position in the array from 0 to size minus 1, and in each position, we'll check and see if that position contains the target. So if array position P contains the target, then we found it, we can quit and just return P, right, the position where we found it. So we'll just return P, and again, that immediately leaves the function, right? It leaves the loop, it leaves the function, goes back to whoever called us and says, here, I found it, position P. Now, if we get all the way through the for loop, if it goes through every position in the array and we never find it, so we never did this return, then by the time we get out of the loop, we go, okay, well, wasn't anywhere in there, I'll return a -1. So we can return the -1 after we're done with the entire for loop. And then in whoever calls this search, whoever wanted the search done, they're calling search, they're passing the array they want searched, they're passing the size of the array, and they're passing the value they want us to look for. Right? The search routine is giving back a position or a -1, and so we're going to store that in a variable someplace. I'm going to call this pause just for position. And so again, once I get that value back, I want to take a look at it and see if they found it or if they didn't. So if pause is -1, they didn't find it. So whatever it is I want to do, if the value is not in the array, I would do it here. Right now, I'm just going to print out, I didn't find it. Otherwise, we're going to do whatever it was we were going to do with that array position once it was found. And again, in this case, all I'm going to do is say, okay, we found it, found the value in whatever the position is. But again, it's pretty straightforward for the call. It's a pretty straightforward function to do our linear search. And again, the drawback with it is that it does look through every single position in the array. Right? If you've got an array of a billion elements, this is going to look through all billion elements potentially. So we want this more effective way to search. And this is where our binary search comes in. We'll talk about the algorithm in just a sec, but again, I want to emphasize that this will only work if we know for sure that our data is sorted. If the data is not sorted, right, if the contents of the array are not sorted, or even if they're sorted but in the opposite direction that we think they are, right, if we think the values are going up, but in fact the values are going down, then this isn't going to work either. So we have to know it's sorted, and we have to know whether it's sorted in increasing order or decreasing order. So what we're going to do is, assuming our array is sorted, this binary search, we're essentially going to say, well, let's keep track of what chunk of the array I need to search. Right? In the beginning, it's going to be the whole array, but eventually we'll start narrowing this down. So I'm going to use two array positions to tell me kind of the first position and last position of the section of the array I still need to search. So I'm going to call them low and high. So low for the bottom position and high for the top position that I still need to go through. And so in the beginning, low is going to be 0, and high is going to be, right, size -1 for whatever size the array is. And then the algorithm is essentially going to be keep searching until we run out of space to search, right, until low gets bigger than high somehow, or until we actually find it. And so what I'm going to do on each pass through this cycle is I'm going to figure out what the midpoint is, what's halfway in between the low position and the high position, and I'm going to look at what's in the array in that middle spot. Now, we could luck out. We could find the target there. We could land on it, in which case we can return that position and say, hey, I found it in whatever the middle position is. More likely, we're not going to find it in this kind of particular cycle, but we can figure out whether it's in one of the lower half positions or one of the upper half positions in the array. If the value that's in that middle position in the array is bigger than what we're looking for, then we know that, because again the array is sorted, we know that the value also can't be in anything above the middle position. Right? If the values are going up and what's in the middle is already too big, then it can't be anywhere higher up in the array. It's got to be in the lower half. So what we'll do is say, instead of our high being kind of whatever the high was before, now we'll set our high to the middle position -1. Right? We know we've got to search somewhere in that lower half. So this effectively throws out half of the array space we've got left to search in that one spot. So if the value is in the middle, then we throw out the top half, or if the value in the middle was too big, we throw out the top half of the search space and just say, I'm going to restrict it to the bottom half. Otherwise, if the value isn't equal and isn't bigger, it's got to be smaller. So if the value in the middle is smaller than what we're looking for, then we only want to look in the top half of that section. We can throw out the bottom. We can throw out everything from position low to position middle. And so we'll just set low to middle +1 instead. So again, this cuts out, every time we go through this loop, it cuts down half of the space we've got left to search. So here we'll actually tackle this as a recursive algorithm. Later on, we'll tackle it as a loop. So here's my binary search function. Right? I'm going to return an integer, same idea as before. We're going to return the position where we find this thing, or a -1 if we never find it. Again, we're given the array that we want to search. We're given a low and high. I seem to have forgotten my target in here to look for. So there should also be a float target in here. So we'll actually write a version of this that works in just a second. So pretend that we've got a float target in there as well. And again, what we're going to say is, for this current call, if low is bigger than high, right, we're supposed to be searching from the low position up to the high position, or somewhere in that range. If low is already bigger than high, then we've got this impossible range. I'm not going to be able to find it, so we'll return a -1 right then. Now, if we get past that, we've got a valid range to search, so we'll figure out what the middle position is. So we'll take low plus high, divide by 2, and that gives us the middle. Again, this is doing integer division, so it's going to drop any fractions, so keep that in the back of your head. And then we'll do those steps that we were saying. If what's in the middle matches our target, we've found it, and we can simply return that middle position. Otherwise, if what's in the middle position, oh my goodness, there's a bunch of bugs in this. If what's in my middle position is bigger than the target, then everything from the middle position to the high position is going to be too big. So I'll set high to middle -1, right? Because I know it's got to be somewhere in that lower half. And then I should be doing a recursive call on my binary search. So we better write the real code for this in just a moment. And then the else case is where what's in the middle is smaller than the target, in which case we want to search the upper half. We want to search from mid +1 up to our high. And we'll do a recursive call using our new low and high. So let's go off and give that a try. So let's write our how about a bin search, and let's stick an R on here for our recursive version. So we'll go through and see if we can get this right. We'll include our IO stream. We'll use our standard namespace. We want our binary search. I'm going to be lazy and just call it bin search. We've got the array. We've got the low. We've got the high, so the range of positions to search. And we've got the target that we want to look for. So that was the first of the goofs from our slide. Let's have our main routine, and in here I said these would be an array of floats. So let's say we've got, I should put a constant here. Let's say my size is, I don't know, 6. And let's create our array of floats. And again, I'm going to initialize it right here just to be a little lazy. And let's say they're 10, 20, 30, 40, 50, 60. So we've got our 6 values, and we'll try a couple of binary searches. So let's look for the position of, so we want to call a bin search on our array, going from position 0 through position 5, right? So we're searching the whole array. And let's say the first time we look for value 30. So hopefully it should find that one. Searched for 30 should be in position 0 and 2. And so the result is, and we'll print out the position. So this will give us a chance to see if our binary search was actually working or not. And then let's do the same thing with a couple of other values. Let's do a binary search on our data, but let's look for a value that isn't in there. So let's look for the value 17. So this should be a -1, right? Not found. And so we'll see how that does. And then let's try one more, see if it finds something on one of the ends. Let's do a binary search and see if it finds the 60. Should be in position 5. So we'll try a bunch of binary searches on this array that we've gone through and created and see if the thing actually works. Now, I suppose we should actually go create our binary search function. And so again, if low is bigger than high, then we'll return a -1. Not possible. Otherwise, we'll compute our midpoint as being our low plus high over 2. And we'll check out to see if we found it or if it should be in the lower half or the upper half. So if what's in the array in the midpoint matches our target, then we can return the midpoint. We found it. Otherwise, if what's in the array in the middle is bigger than our target, then we want to go through and search the, if what's in the middle is too big, we want to search the bottom half. So we'll say our high is equal to our midpoint minus 1, and we want to search from low to that midpoint minus 1. So we'll do a recursive call of our binary search using the same array, using the same low, and using this new adjusted high and our same target. Otherwise, it's got to be in the upper half, so we'll set our low to our midpoint plus 1, and we'll do our binary search on our updated low and high and target. So again, it's got to be in the bottom half because what's in the middle was too big, or it's got to be in the top half. All right, so there's the theory. Let's see how we do in compiling this beastie. Our bin search r.cpp-o bin srx. Why not? Ooh. All right, let's see if our bin srx actually works. Searched for 30, should be in position 2. It found it in position 2. Search for 17, should be a -1, not found. Oh, result was a -1. Search for, hey, it actually appears to be working. Now, just so you can see what's what's taking place here, let's throw one extra thing into our binary search just so we can see the sequence of calls that are being made. So let's just say we're in our binary search, low is, and we'll print out the low value, high is, and we'll print out the high value, just so that we can see with each recursive call what range is being searched. So let's run it. And so again, for each call, we're seeing our, here we are for our first call to binary search. And in this case, it happened to luck out, right? We called binary search, low 0, high of 5, so we said search the entire range. This was the call from, this was the first call from the main routine. The midpoint was 2, and it just happened to find the 30 in position 2, so it found it right away. So this one is our second run of binary search, where we said look for 17, that's not in there. So it called on the range 0 to 5, took the midpoint, which was position 2, which was a 30, and said, oh, okay, well, what's in position 2 is too big, so I've got to search the lower half. So it searched from the section 0 to 1. And I guess what was, so in this case, the midpoint would have been 0 plus 1 divided by 2, rounding down, so it's going to be 0. So it looks in position 0, sees the 10 there, and says, ah, that's too big. So it makes a recursive call going from positions 1 to 1. And so it, the midpoint of 1 to 1 is going to be 1, so it looks in position 1, which is a 20, and didn't find it there. The 20 is too big, so it does a recursive call from our low of 1 to our high of 1 less than the midpoint, which is 0. So that final call goes from 1 up to 0, which is why that first test we had for, if we're getting our range incorrect, means we didn't find it. That's where it returned our -1. Right? So you can see this cycle where it gradually winds its way down until eventually either it runs out of space to search or it finds the thing you're looking for. And again, that third example where we were looking for the thing that was right on the end, right? It was looking from position 0 to 5, looks in the middle, position 2, the value there was too small, so it looks in the upper half of the array, so now going from positions 3 to 5, looks in the middle of that, so that would be position 4, and what's there is too small, so it looks in the upper half of that, so going this time from positions 5 to 5, and of course it happens to run into it there. So at that point it figures out, I found 60 in position 5, and it gets returned and returned and returned, and we get our answer. So this does actually work out. All right. So this is a sample call pretty much like we just used, where we're going through and saying, okay, let's call a binary search, pass it the array, pass it the range we want to search, and pass it the thing that we want to look for, and either we find it or we don't. Now, the nice thing about binary search is that because it discards half of the space that's left to search, every time it makes a call, then in n successive function calls, it can search a space that's pretty much equivalent to 2 to the n array elements. So in 10 calls, we can search more or less 2 to the n elements, which is roughly 1024. And in 20 calls, we can search roughly 2 to the n spaces, which in this case is 2 to the 20, which is, again, roughly 1,000,000. In 30 calls, you can search roughly 1,000,000,000, right? 2 to the 30. So this is very effective at searching very large arrays for a value as long as we know the array is sorted. So, much more efficient approach. All right, I did want to touch on the iterative version. So this is doing the same thing, but with a loop instead of with recursion. So we've got the same kind of idea where we've got our low and our high, right, going from 0 to size minus 1 in the beginning. So this time around, our binary search only needs the array, its size, and the target. Right? It doesn't need to be passed the low and the high. It can figure out low and high if you give it the size. So we figure out our initial low and high, and then again, we just repeat. We keep going as long as low is still less than or equal to high. Compute the midpoint. Check to see if we found it, and if we have, return the midpoint. Otherwise, if what's in the middle is too big, then we search in the bottom half. We adjust our high to be our mid minus 1, and otherwise, what we're looking for must be in the small half, so we adjust our low to be the middle plus 1. So it's the exact same logic, just plunked into a loop instead. And of course, this has the advantage of not doing those recursive calls. So we can quite happily use either approach for our binary search. Sometimes the logic is a little bit more obvious for the recursive version. On the other hand, you might be more comfortable working with loops, and the looping approach is going to be a little bit more efficient. So we've got our binary search if we know the data is sorted. But that means that, unless we happen to luck out and the user gives us the data in sorted order in the first place, it means that somebody gives us an array full of information and we then have to turn around and sort it. So that's what we'll take a look at next. I'm going to look at a really straightforward sorting algorithm called bubblesort. And the way this works is we're just going to go through the array again and again and again. Each time we're going to go through it from the beginning to the end. And as we're going through it, we'll compare the element that we're sitting on right now with the one beside it. And if those two things are out of order, then we'll swap them. If we've got a 3 and then a 1, then we'll swap them so that it's a 1 and then a 3. And then we'll proceed on to the next element in the list. So we'll just gradually work our way up, looking for things that are out of order. So by the time we get to the end of the array, things will be closer to the right order. Right? Some of our values that were out of order before will now be in the right order relative to one another. But if I had something like, if I started with, let's say, 10, 1, 2, 3, 4, well, I shouldn't pick that. How about 10, 20, 1, 2, 3, 4. How about that? So it does that first comparison of the 10 and the 20 and says, oh, those things are okay. And then it moves on and does the comparison of the 10 and the 1 and goes, oh, the 20 is bigger than the 1, we'll swap those. So it moves the 20 up and the 1 down. Then it compares the 20 and the 2 and moves it up, compares the 20 and the 3 and moves it up, compares the 20 and the 4 and moves it up. So what's actually happened at the end of that first pass is the 20, the biggest value in the array, has made it all the way to the end. So we're closer to the right order, but that 10 is still sitting way back at the beginning because it started off stuck behind the 20. So we have to go through the whole thing again, trying to get that 10 working its way up to its right spot. So what actually happens if we do this is at the end of each pass, kind of the next biggest value will have reached its correct spot somewhere up in the array. Other things might have also made it into their correct spot, but we're guaranteed that after one pass, the biggest thing will be in the right spot. After 2 passes, the 2 biggest things will be in the right spot. After 3 passes, the 3 biggest things will be in the right spot, etc., etc., etc. So we gradually work our way towards a sorted array. So again, this is just working through a simple example here. Let's say we've got 3, 17, -1, and 8. So this first pass, we compare the 3 and the 17 and say, okay, those are okay. Those are in the right order compared to each other. So you move on and compare the 17 and the -1 and go, okay, well, those are in the wrong order. The big thing is first and the little thing is second. So we swap them. And so now we wind up with the 3, 1, -1, and 17. And then the 8 still up at the end. So now we move on and consider that next pair, the 17 and the 8. And you go, oh, okay, wait, those are in the wrong order, so we swap those. So at the end of our first pass through the array, it's closer to the right order. We've got 3, -1, 8, and 17. So we make a second pass. We start way back at the beginning again and compare those first 2 values, the 3 and the -1. Well, they're out of order, so we swap them. Right? So now we've got -1 and 3, and so we go through and compare the next two things, 3 and 8. Well, those look okay. And then we go through and compare the next two, and those look okay. And in fact, at this point, the array is sorted, but we don't really know that for sure yet. You just keep making passes like this until eventually you get everything sorted. So let's take a look at a simple implementation of that. But throughout this, I'm going through and saying, well, if a pair of values are out of order, we need to swap them. So if you recall, we looked at a swap function way back when. So let's just revisit that. So a function to swap, in this case, two floats. So we'll take two floats passed by reference, and all we're going to do is exchange their values. So we'll store what was originally in x. We'll store that in a temporary variable. So I'm just going to create a variable named original x and store x there. Then I'm going to take what was in y and put it in x. And then I'll take what was originally in x and put it in y. So I've exchanged the two values. And we'll call this swap routine in our bubble sort. So let's look at a first basic version of our bubble sort. So for this one, again, because after one pass, at least one biggest thing has made it to the right position. After two passes, the two biggest things have made it to the right position. After n-1 passes, the n-1 biggest things have made it to their correct position. If there's only n elements in the array, and the n-1 biggest things have made it into their correct position, then you've only got one thing left, and it's still sitting at the front of the array, and so it's the smallest thing, and it's in its correct position as well. So in fact, if you've got an array of n elements, you make n passes through this, you're guaranteed to be sorted. So that's what we're going to do here. We're going to make n passes through the array, and on each pass, we're going to go through comparing those pairs of elements and swapping them if we need to. So my pass here for the first loop is just counting which pass number I'm on, and it's going to go from 0 up to our size -1, or well, we're less than size -1, right? So we get size -1 passes. So we've got our outer loop is just saying make essentially our n-1 passes through the array. And then on the inside, we'll just compare each pair. Now in this example, what I'm going to say is I'll start off in position 1 and compare what's in position 1 with what's in the spot before it, position 0. And then I'll move up. So I compare what's in position 2 with position 1, then compare position 3 with position 2, and then 4, etc., etc., etc. So we'll keep going until we hit kind of the spot for the last pair of values. So each time through, we're going through all of the pairs, if you like, and each time through we're comparing what's in the current position with what's in the position before it. And if the bigger thing is first and the littler thing is second, we need to swap them. So, and I've got my logic around here. Oh man, I've got to do some corrections in this batch of slides. So, if what's in the smaller position is bigger than what's in the bigger position, then we need to swap them. So I must go correct my bubble sort slides too. All right, and again, that just goes through over and over and over again. Eventually we wind up with a sorted array. So again, we're going through, if things are out of order, we swap them. Right? We go all the way through the array, doing all those swaps for the current pass, and then again, we just keep doing passes until we're guaranteed to have the whole thing sorted. Now, this works. Once you correct a less than to a greater than here, this works, but it's very possible that this is doing a lot of extra passes. Maybe there was only one or two things that were out of order, and we got those in the first couple of passes. And all the rest of the passes, we've just been wasting our time sorting an array that was already sorted. So our second version is going to try and improve on that a little bit. In our second version, on each pass, we're going to keep track of whether or not we had to make any changes. If I go all the way through the array and I don't find anything out of order, then it's sorted. I don't need to make any more passes. So I'm going to have this Boolean variable sorted that's keeping track of whether or not the array is already done. And I won't know that until I've already gone through it and found nothing to change. but that's the idea. So I'm going to keep going through while the array isn't sorted yet, or while I don't know it's sorted yet. So each time through, I'll say, okay, well, I think it's sorted, and I'll change my mind if I find something out of order. And so then we go through each pair of values again, and if something is out of order, right, if what's in the array in the smaller position is bigger than what's in the array in the bigger position, hey, at least I got my greater than right this time, then we'll say, I had something that was out of order, so it wasn't sorted on this pass, it still might not be sorted, so I'll set sorted to false, and I'll do my swap, and again, continue on. So we'll go through this over and over and over again, just checking if we need to swap anything on this pass through the array. Now, there's one more thing we can do to kind of try and speed things up. I said that after one pass, the biggest thing is already in the top position. After two passes, the two biggest things are in. So when we're making a pass, if we know how many passes we've already made, we know that the stuff at the end of the array is already sorted. And so we're going to keep account of how many passes we've made, and we'll stop, on our current pass, we'll stop before we get to the section that we know is already sorted. So each time through, we'll be looking at one fewer pair than we did the last time through. And so those are the two kind of optimizations that we're making here. Each pass, we're stopping sooner, and if we make a pass that doesn't find anything out of order, then we're done, and that's the last pass we'll do. So again, these are, in the worst case, this is still going to perform the same as our original version. If, for instance, if somebody gives us an array where all of the elements are in absolutely backwards order, then the two of them will still take the same amount of time, and it'll basically be n squared over 2 passes, or n squared over 2 operations in this thing, and n squared over 2 swaps before this finally finishes. But an awful lot of the time, this version should stop earlier than the other one did. So we've got our bubble sort that we can play with, and we've got our binary search that we can use if we know it's already sorted. Let's just take one more moment to take a look at how we can test to see if an array has already been sorted or not. So somebody passes us an array of data, and we want to do things with it, but we're not sure if they sorted it or not. So we're just going to run a quick function here to go through and check the contents of the array and see whether they're sorted or not. So this one we're checking to see if it's sorted in increasing order. So again, somebody passes us our array, they pass us the size, and all we're going to do is that pairs idea. Again, we'll go through each pair of values, compare each thing with the thing after it, and if they're in the correct order, so far so good. If they're out of order, if the bigger thing is first and the smaller thing is second, then we already know that the array is not sorted because we found a case where something too big is before something too small. So we'll just go through our pairs. So starting from position 0, and while we're on position sort of size -2 or less, we'll compare what's in our current position with the thing after it. So that's why we're stopping one spot earlier, right? We're comparing what we're on now with what's next, and we don't want that next thing to be off the end of the array. So if those two things are out of order, if the bigger thing is first, then we'll return false. We don't need to look any further. We've already got proof that it's not sorted, and so we'll just bail out now. If we get through all of the pairs and nothing was out of order, then it is sorted, and we can return true. All right, so that's our grand glorious introduction to sorting and searching. And again, these kinds of ideas, these kinds of algorithms, these kinds of processes for going through and doing things like sorting or doing things like searching are something that we'll work with more and more, where we've got some kind of a data collection that we want to operate on, and we're looking for an efficient way of doing that. So that is our first introduction to some of our more interesting algorithms. All right, I will leave that there for now. And personally, I'm going to run off and go fix those slides and reload the corrected slides, but that is my problem. Bye, folks.